Hello again, everybody. Welcome back to an exciting day 3 of e-learning. You'll see at the top here we are still continuing on with polar coordinates. Yesterday we did some graphing of them. We took some derivatives of those. Today, you can read. At the top of the page we'll be doing integration and how we can handle that with polar coordinates. As a little heads up, if you've looked online, maybe you've already seen this, but I did manage to get a quiz created, similar to what you would have taken in class on Thursday. So this coming Thursday, be prepared to take a quiz online. A couple things about that quiz you'll want to know is that you can only access that quiz Thursday between the hours of 9 a.m. and 3 p.m. And once you start it, you will have only 45 minutes to complete it. That should be plenty of time, but just make sure you are aware of that. Make sure you know what you're doing so you're not fumbling around. Obviously, you would have notes in front of you if you have taken them over the last few days. It probably won't give you a ton of time to just rifle through all those and take all the time you want trying to figure those things out. So you do want to come into that quiz somewhat prepared so that you can get that done in that 45-minute time period. Certainly we'll need your calculators to make sure that those are readily available, and that's going to be tomorrow. All the directions for how you would access that is on Skyward. Follow those directions, and then hopefully everything will work out fine. So you'll see at the top what we're going to be doing today, integration in polar coordinates. A lot of words up here. What this is really kind of setting up is the idea that if I gave you a circle, so let me draw in our circle here, with, let's say, a radius of 4, and I ask you what is the area of the circle. So if we wanted to know what is the area of our circle, if I know that radius was 4, then pretty simply the area is going to be 16 pi. So that's the area of our entire circle. What this is dealing with, what this idea that we deal with today is based off of, is the idea of the area of a sector. A sector, so let me get rid of this, is just a portion of our circle. So just to make this some nice numbers, I'm going to go up here. What do I want to pick? To 90 degrees. And let's say we just wanted this area. Pretty simple. You can do this largely in your head, but just to kind of set up where this formula for the area of a sector would come from, what we would want to do is take the overall area of 16 pi, and then we can compute this pretty easily in our head. We would want 1/4 of that, but the reason that's 1/4 is you would take whatever the degree measure is of our sector. So since we're going from 0 to 90 degrees, our degree measure of that sector would encompass 90 degrees worth of the circle. The full circle would be 360. So if we divided those, that would tell us that we would want 1/4 of 16 pi. Area overall then is going to be 4 pi. Okay, so that's where this area of a sector comes from. I use degrees. I think it's easier to see. But what we really did is we took the angle, we divided it by 360 degrees. So our angle's theta. We're obviously doing this in terms of radians. So instead of 360, we would use the 2 pi. We then multiplied that by the overall area. For us, it was 16 pi. When we got that for us, it ended up numerically being a 4 pi. But if we don't know all of these values, it gives us this little formula here. Not sure if you do that anymore. Math 1, Math 2, Math 3, not terribly important. It's not terribly difficult. But if I ask you to find the area of a sector, that's how you would do that. 1/2 times our angle times our radius squared. So that's the basis of what we're going to be getting into. So when this at the bottom here says find the area of the region below, sketch in one of our cardioids that we drew the other day. And let's say that I just wanted you to find the area between, let's say that's 0 and pi over 3. So the shaded area in there. We can try and set that up. The 1/2 theta times r squared. So 1/2. Our angle, since I told you this is going to be pi over 3, so we would multiply by pi over 3. But our issue is going to be, unlike a circle, where we talk about a radius, where the radius is going to be the same all the way around, pretty clearly at angle 0, our r that we would have drawn out is longer than what our r is at pi over 3. They're also different than what they would have been at, let's say, pi over 6, pi over 4, pi over 3, all these angles in between. Our r is changing now, it's not a circle. So it is hard for us to just plug that in. So what we would really kind of need to do is understand that since this is constantly changing, that this is going to be a variable expression. For us, this is typically pretty easy, but understand that's just going to be our variable expression for r. Similar to an integral where we need to add up a bunch of them, what we would want to kind of figure out is what is the area in here, what's our area in here, what's our area in here, add them all up. Hold on just a second, I got my 2 banshees running wild. All right, so that when we start breaking these up into smaller sectors, it gets into the idea of a Riemann sum, adding them all together, finding out what happens as, you know, our angles get closer and closer together. So that's kind of walking you through this down here. Now the region is bounded on the top and the bottom by angles. All right, theta sub 1, theta sub 2. It is bounded at the top by the radius at whatever angle we are looking at. So since the radius and the angle will change, we refer to this as kind of r sub k and then theta sub k. We can approximate the area under the curve by setting up a Riemann sum of 1/2 r squared and then our change in theta. So I could do 1 from 0 to pi over 6, but obviously that's not going to be the same radius that entire time, but it's a small angle. We could approximate that. We could do it every 30 degrees, so then we can go pi over 6 to pi over 3, so that would kind of be our change in theta. Ideally, though, we want the change in our angle to be as small as possible, so there's as little error as possible. That gets into this whole limit of our Riemann sum, gets us into our integral, so that's what this is, 1/2 multiplied by whatever our function is that's constantly changing the radius, multiplied by what our d theta would be. But if we make our change in theta smaller and smaller and smaller, so apply the limit, if I can get this to right, the limit as the delta theta goes to 0, then what this ultimately would turn into is this definite integral, where you're going to have your 1/2 r squared theta is normally our formula. If we look back up here, you'll see the 1/2 in both. You're going to see your r squared in both, but then our theta is changing, and what we would want it to be is ultimately the change in theta to be really, 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 really small. So we get rid of the delta theta, make it our d theta, and then what we need to know is we're looking for all the r lengths, all the step lengths when we've graphed these over the last few days over whatever limit of angles that we are going from. So in the problem above, this would have been 0 to pi over 3, because that's the change in the angle, and we're looking for all the radii between 0 and pi over 3. So when we set these up, we're really doing this. So think of this as the integral is a sum, and what we're adding together is a whole bunch of sectors, and those sectors are always defined from one angle to the other. The d theta is just saying those angles are, the difference in the angles is pretty much nothing, which then should give us the entire sector overall. Hopefully that makes sense. I don't know how well it's kind of hard to explain on this. This is probably not necessarily hardest to do, but it's the hardest kind of explain and for everybody to see. So Monday of next week, if we see you, or at least Monday after spring break, if I see you, will be just dedicated to questions. Test would be on Tuesday, so if you're not squared away on some stuff, feel free to speak up then. So what this starts out with is these are actually pretty simple. What we are talking about at the top here is the area when we're defining in polar as a sector is 1/2 times r squared multiplied by d theta. So we graphed them yesterday, so hopefully you went through that, you looked those over, and what we found is if we wanted to graph this entire curve, we would have to set up our little r theta chart and start at 0 and then just work our way all the way through. We talked about symmetries to make sure that we can make this a little bit shorter, but if we really wanted this entire curve, we'd have to plot every angle between 0 and 2 pi, figure out what all the corresponding radiuses are, radii are. But for the sake of these, that makes this pretty simple. So what I really want are all the r lengths, all the radii length, and we know what r is in this case. It's the original equation here. 1 plus cosine of theta doubled. So this is our r squared. So we have 1/2 r squared. And our change in theta for us just has to go from 0 to 2 pi. That's the integral that we would then set up. And then certainly, so quiz tomorrow, you'll have to do a few of these. This definitely now is very much dependent upon our calculator. So we throw that into our calculator and should get 6 pi or whatever that is. Let me see here. My calculator as a decimal. Throw that in. $18.850. All right. So really just 1/2 r squared d theta. It's kind of like when we did discs. We were just finding the sum of circles. Now we're doing the sum of sectors. We know what the sector is, 1/2 r squared theta. The theta is our limits with the d theta. So now yesterday we did these where I would have had you graph this. So this is something that you would probably want to graph on our calculator. So this is something that you will want to definitely be able to do on your calculator, is to graph r2 cosine of theta plus a 1. You don't want to rely on what this might look like or having to do this by hand. So the way you're going to have to graph this, let me write little notes over here. You'll go into your mode. So on the calculator, if you type mode, first step, we've already changed. I've already shown you how to do parametric mode. So function mode, you're usually in almost all the time. We've done parametric mode. We now are going to go to that same spot where we moved to parametrics. So mode, go on down where you see function, and then where it says parametric, the next one over says polar. So if you go to polar, highlight that, hit enter, and then hit your y equals key, what you're going to see when we go to graph, you no longer see y sub 1, you're going to see r sub 1, r sub 2, r sub 3 on the calculator screen. And for us to graph this, you will just do 2 cosine of theta plus 1. And you'll see the cool little theta will now pop up when you hit the variable key. And then what you are going to see when you graph that now is one of the ones that we did yesterday by hand. Except we don't have to do it by hand right now because we have our calculators. So that should look like this, roughly. And you'll see that little loop that we did yesterday when we graphed. And what we're looking for is the area in here. All right. So we definitely have the area of a sector still. It's based off of that. So you're going to have your 1/2. You're still going to have your r squared and then multiplied by your d theta. R in this case, again, these are all pretty straightforward. R is this 2 cosine of theta plus a 1. What we need to know is what angles do we need to be adding all of these r lengths up in between. So this is based on yesterday, so we had to kind of understand what we did yesterday and look this over yesterday. When we graph these, the reason we got this little loop in here is because as we were going through our angles here, so starting at 0 and then, pi over 6, whatever, eventually what happened is one of our angles would have given us a radius of 0. And that's why we would have, as we were working our way around here, the reason we got a loop is because we had a radius of 0. We continue to work our way around. Let me kind of do this in red so you can see this. We continue to work our way around this loop. And if you remember, the reason we're working our way around that loop is we were looking kind of out here at pi and all these second and third quadrant angles, but we were given negative r's. So then we get a bunch of negative r's. So I don't know, make these up, whatever you want. But eventually, as we worked our way around and out of this circle, we would have gotten back here. So there would have now been another angle that would have given us a radius of 0. So what we need are these two angles right here. The angle that would given us an r of 0 to get us into the little loop, and then we had all the negative angles or negative r's in between, and then eventually what angle would have gotten us out. So what we're really trying to figure out is, when did our r equal a 0? So this is our r. When did we get values of 0? So what we just do is take this equation. This is r, so r equals 2 cosine of theta plus a 1. And what we really need to figure out is, when did this r here, get rid of that, equal or give us a length of 0? Little trig equation, that's what we finished up with yesterday. So if we subtract that 1 over, divide by 2, we have the cosine of theta set equal to a negative 1/2. We want to solve that real quick. So if you think about our unit circle just in general, the angle where our x coordinate is a negative 1/2 would have been what, 2 pi over 3? And then the other place where our x coordinate has an angle, or the angle whose x coordinate would have been a negative 1/2 is down in the third quadrant. That pi over 3 angle is 4 pi over 3. So we really got to know our unit circle pretty well with these. If those are our angles, that then tells us we can now go up to here, and we know our lower limit is the 2 pi over 3. That's the angle that would have gotten us in there. That's the second quadrant angle. And then our upper limit would be the 4 pi over 3. So we're going to find the area of the sectors, all those little r's that's created by that radius between the angles of 2 pi over 3 to 4 pi over 3. From there, throw that in the calculator. Let me create some space here. Get rid of all those. Throw that in your calculator, and that should give us an area of 0.544. All right. 3, similar, just make sure we understood what we just did there. This, graph that into your calculator. What this one should now look like is just one of these vertical, that's bad. One of these vertical ones that have a loop in it. Try doing a little bit better here. Oh man, so I think it looks like this. A little bit better, not terribly embarrassing. We were looking for this area in here. So one more quick little explanation is we would have been working our way around this cardioid. Eventually, all these r's are positive, that's why we're sticking out, but eventually we get an r that's a 0. Then as we move around the loop, we eventually would get out of the loop when we get another r of 0 as we then get our way out. So the loop would have been created from when did r equals 0 the first time through when did r equals 0 the second time. So that's our step. We're going to take this equation here, set r equal to, our equation equal to 0, let r equal to 0, solve this. So similar setup to the previous one. We're now just trying to figure out where did the sine of theta have values of a negative 1/2, and then you'll see we'll be chilling out down here in the fourth quadrant in terms of where our y's are going to be negative. So the y coordinate in the third quadrant or the angle in the third quadrant, whose y coordinate would be a negative 1/2, should be, I think that myself, y coordinate, third quadrant. Should be 7 pi over 6. If we go to the fourth quadrant, the y, or the angle whose y coordinate is a negative 1/2 in the third quadrant should be 11 pi over 6. So some little used angles now that we're going to have to be recalling. Area then we know is 1/2 of r squared multiplied by r d theta. R is 1 plus 2 sine of theta. We now know 7 pi over 6 would have gotten us into the loop. 11 pi over 6 gets us out of the loop. All the angles in between would have been the negative values of r that give us the loop. Throw that into our calculator. It's pretty much the same exact problem as the previous one, just made you solve for some different angles. You get the same answer, 0.544. Last thing with this polar that we would need to know is the area between curves. It is similar, yet also got something different with what we would have done before in regular function notation when we were doing area between curves. So that's what it says. Very similar to finding area between the curves using Cartesian coordinates. So number one, find the area enclosed by the two curves. Then we need to find the intersection points like we did before. That would be in terms of theta. What's going to be different about this now is the area of this. It's not always top, bottom, or right, left. It is the outside curve minus the inside curve. So again, let me try to explain this here. At school, it'd be a little bit easier. But when we would have done washers, or discs or anything, we always did the top minus the bottom. Or we would have done the right minus the left. The reason we do those is what we're really doing in this instance and this instance is top is bigger than the bottom. So we did the bigger minus the smaller. Hopefully that's supposed to say smaller. The reason we did right minus left is because the right hand side is our bigger side and the left hand side is smaller. So it's the same in the sense that we always want to be doing whatever the bigger value on the curve is minus whatever the smaller curve is. But in polar, whichever curve is on the outside, farthest away from the origin, that's your bigger curve. And then the inside curve is obviously then going to be your smaller curve. So in some ways, it's going to be similar. So let me draw a couple of examples, and then I can show you how it's similar in some instances and going to be different in others. Let's say I gave you two different polar curves. So let's say we have a circle, and then I gave you a cardioid that looks like this. All right. If this is the area that I was looking for, then it's going to play out pretty similarly to what we have done before, where this is the outer curve, this is your inner curve. It's also the right side minus the left side. So right minus left would be very similar, pretty much the exact same thing that we would have done before. All right. However, let me give you one that would be a little different than that. Let's say we have that same circle, like so, but our cardioid goes out here. And the area we are looking for is this one. When we are in polar, if you haven't noticed, everything we do is measured from the origin. So if I look sort of in this direction, let's call this R1, let's call this circle R2. It's pretty clear then that R1 is the bigger value. Let me try blue here. Than R2, because if I go to R2, I only got to go that far out. So bigger minus smaller in this instance would actually mean we're going to be doing this outer curve. So this one here is our bigger one, minus this smaller one. So it's kind of different than what we would have done before, because now you're doing left minus a right. All right. So the big thing you have to understand is we're always doing bigger minus smaller. The outside curve has the bigger R value than your inside curve. When we do that, then, if you look down here at the formula, what we would basically be doing is, if we kind of just cross that out, if I just did from whatever angle to whatever angle 1/2 r squared d theta like we would have done before, let's say it was this one, that would give us all of this. Well, we're not going to want all of that because we don't want the area inside of the circle. So what we would then want to do is subtract away whatever that area is. If I can get this. And if we then subtract away that inner circle, that should give us everything that was in between. Okay? Hopefully this is making some sense from a distance. All right, so number one, you could use your calculator if you needed to. You certainly probably will when we do a little quiz on this. This one we should know. We should definitely be able to graph that out without the calculator. That is a circle with a radius of 1. Draw that in. And then if you took out your calculator and you graphed 1 minus the cosine of theta, that would look like this. Pay attention to how this is worded. If you look at number 1, if you look at number 2, number 1 you'll see r equals 1, number 2 you'll see r equals 1. Number 1 you're going to see r equals 1 minus cosine. Same with number 2, 1 minus cosine. But if you look, I want to be inside the circle in number 1, but outside the circle in number 2. So we have to read it carefully, know what we are actually looking for with these. So for number 1, we are going to do inside the circle, but outside of the cardioid. So if we look at this graph, we have region 1 here, region 2, region 3. The region that satisfies those two conditions, you're inside the circle, but outside of the cardioid, would be region number 3. This is what we are looking for. Okay? So when we know that, we can go ahead and get this started with 1/2. And then we've got to do r squared, big R squared, minus the little r squared. But now we're thinking the outside curve and then the inside curve. So if this is our origin, the curve that's farther away from the origin that's creating the bigger r is our circle here. So the circle needs to go in first. So we write the circle that had a radius of 1. The inside curve then is, if I can squeeze this in here, the 1 minus cosine of theta. Multiply that by your d theta, and the d theta is kind of the key one now because we now need to figure out what angles these are. So it's similar to what we would have done in the past. We really want to know, if you notice, those 2 points here and then here, the reason they are intersecting is because at whatever those angles are, their r's would have been the same. They're equal to each other. So similar to what we would have done before, we're going to take these two equations, r equals a 1, 1 minus cosine of theta. We want to know when do the r's equal to each other and what angle would that occur. So by setting those equal to each other, you'll see the variable that's now in play for us to solve for is our angle, our theta. So if we went ahead and subtracted your 1 over negative cosine of theta is 0, multiplied by the negative, we're really just looking to figure out when did cosine of theta equal a 0. Those angles then would be at pi over 2 and 3 pi over 2. So now, here's where you want to be careful, another place you want to be careful. One of our most common mistakes with this. You have to understand that if I use these angles right now and go from pi over 2 to 3 pi over 2, we're not going to get the right answer. Think about what the integral means. From pi over 2 to 3 pi over 2, we're going to be finding all of these r values for every angle between pi over 2 and 3 pi over 2. So if you think about what that means, here's pi over 2. Here are all the angles in between pi over 2, 3 pi over 2. We don't want the values over there. That's not what we want. We want, if I can get rid of these, that's annoying. What we want are all these values over here. Oh, crap. Let's see if I can go backwards. There. So we want all of these angles over here. So sometimes people will ask, all right, well, can I put 3 pi over 2 here and put pi over 2 here, thinking that that would take us from here to here. Think about what that would, though, mean. If I can go backwards then. So let's go back to where this was pi over 2. And this was a 3 pi over 2. If you remember, only thing that happens when we flip our angles are our limits. So if I just went ahead and switched the pi over 2 with this 3 pi over 2, I get the same exact value. It's just the negative of that. That's the only thing that happens when I flip my angles around. So what you have to be careful of is with these angles, we're not really going to use pi over 2 and 3 pi over 2. We want to make sure that we're always going in the direction of the unit circle. So when we graphed those yesterday, that was always the case. We're always going in this direction. So the way we're going to have to label these is we're going to have to change this 3 pi over 2 into a negative pi over 2. So that if I then go to my limits, and instead of going pi over 2 to 3 pi over 2, I instead start down here at a negative pi over 2, and then make my upper limit the positive pi over 2. Then we go in the direction that we want. We'll go negative pi over 2. Then we'll get this negative pi over 3, negative pi over 4, negative pi over 6. Then we hit 0, positive pi over 6. We get all these angles in here that we need. So be very careful with our angles. When we solve these, we are definitely, as you can see in this very first problem, going to have to rename some of our angles a negative to make sure that we're going in the right order. Okay, so then we take that, plug it into our calculator. Those can be a little bit messy, so do be careful with those. Let me see what we get here. Plug that in. And let's see. Should give us 1.214. Let me create some space in here so we can see all this. It's hard to write small with this online pen. So our area then, 1.214. Okay. So now in this very next problem, same exact graph. So if we look at these two, here's, your r equals 1, I erased an accident. The cardioid is over here. What we now want, though, let me try yellow. We want it to be outside of r equals a 1, but inside of the cardioid. So what that now gives us is this region over here. So no real reason to regraph. I like that a little bit. It's the first time I've used that one. I like that. We're going to go ahead and set up our new integral for this one. So now you're going to do 1/2. You still have that. You'll still have your r squared, with the first one being the outer term, minus the other r squared, with that one being whatever your inner curve is, multiplied by our d theta. Outside now, again, outside is always measured from the origin. So now as we look over here, if we kind of draw on our radius, this curve is giving you bigger r values than this curve. So the outer curve is now the cardioid. So you're going to put the 1 minus cosine here, if you can read that. And then we will put the 1 here. Let me make that a little better. Okay, we need our angles. Now we do want to go in what we had originally found down here for our angles when we set those equal to each other. Now we do want to go from pi over 2, because that'll start us here. And then as we work our way around in this direction, we do want to go from pi over 2 to 3 pi over 2. So now those are the limits that we use. No tricks with that one. Okay, throw that into our calculator. and I get 2.785. So do that, plug those in a couple of times. You may even want to confirm that. A lot of stuff there, but pretty sure I didn't plug anything in wrong for that one. Last couple, next page. This one we could actually graph without our calculator. You could use it if you wanted, but if we understand some of these conversions that we need to know, we have the circle with a radius of 6. So this is up here at 6, this is 6. If we went ahead, divide over that cosine, so what we would end up with is 3 is equal to r sine of theta. That's just a different way of writing that equation. This is y equals 3. It's one of our conversions from the other day. So this is our r equals 3 cosecant of theta. We're looking for that region in there. Okay. We want to be inside of the circle. I guess I've already shaded it. Inside the circle, but above the line. So that's why I shaded where I shaded. So we're going to go ahead and set this up. We're going to have our 1/2, and then our big R squared minus our little r squared. So here's our origin. The farther away points as we look through here are our circle. Again, outside minus your inside is what we're now thinking. It doesn't matter what's on top, bottom. It's the outer one minus your inside one. Make that better. So outside curve, inside curve. So for this one, the outer curve is the circle, 6. The inside curve is 3 cosecant of theta. We need to figure out where they intersect. What angles are we looking at here and here, where they would end up with the same lengths for their r's. That's what would cause them to intersect. So we set them equal. So where does 6 equal 3 cosecant of theta? So if we went ahead and solved this, this is really just 3 over sine of theta. Oops. So multiply the theta over, or the sine of theta over. That would then equal 1/2. And then what we're thinking of, we're in the first quadrant and in the second quadrant, what angles have y coordinates of 1/2? That would be pi over 6, 5 pi over 6. So then those are our angles. Plug that into our calculator. And we should get 22.111. All right, and our last one, put this one last, just so we can kind of distinguish between when we're given 2 different curves. So here we're given 2, inside of one, outside of the other, vice versa. The first couple that we started with, we just had this one curve, and all I'm asking you for is the area. That's actually very pretty, if you would ever want to throw that into your calculator. We can create all kinds of cool shapes when we're in polar. So if you were to graph that, pretty neat. Definitely looks like a flower. A lot of petals running around all over the place. But what makes this pretty simple is we don't have to worry about intersection points. If I just want the overall area, it goes back to when we graphed these yesterday, what we talked about with the first couple of problems today. If I just run through my unit circle from 0 ultimately to 2 pi, figuring out all the r's in between, that's going to trace out the entire circle. So that's what we're going to do. We just have to set up our limits from 0 to 2 pi. So this is the basic one from the beginning. Your area is 1/2, 0 to 2 pi of r squared. We know what r is. It's the equation that you would have been given, times d theta. And we should get 14.137. So that will conclude our 3 days on polar. Again, I do have a quiz made up for tomorrow. You will definitely have to do these, so look them over. know how to plug them into your calculator, know how to graph them. Be prepared. You'll have 45 minutes to do that quiz tomorrow. That should be enough time. It's largely the same quiz that I would have given you in class. For the most part, you do not have to sketch one of them out by hand because there's just no way for me to be able to have you do that and submit it. So that will save you a little bit of time from what our normal quiz is. So I don't think this should be a problem for you to finish. But do that tomorrow. You can only do it tomorrow. And good luck. If you have any questions, reach out, let me know, and I'll try to get you squared away. All right, enjoy your day. See you guys.